Okay, we're going to start today's seminar, APCTP seminar on condensed matter physics. Today's speaker is Professor Gil-Ho Lee, and he's going to talk about new conformation of high order topological state in the tungsten telluride. And just one more announcement is that today we're going to have another interesting seminar on condensed matter physics starting at 5 o'clock this afternoon. Okay, please enjoy the seminar. Okay. Thank you.
Right, thank you very much. I really appreciate this opportunity to give a seminar, and thanks to the APCTP and Professor Yunkyu. So my name is Gil-Ho Lee, and I'm working on the low temperature quantum transport experiment. So please aware that I'm not the theorist. So
we know, don't worry.
So today I want to talk about the tungsten dietal and the superconducting Josephson junction made with this. So this work mostly done by Mr. Yongbin Choi, one of my grad students, and with many collaborators, theorists at HKUST, Big Law, and this Chris Grower at Max Planck, Mas Ali, and also I want to thank Professor Hoo-Jung Lee, who actually provided all the experimental resources and the senior students for this work to be done. So I learned that there is a topological material called Weil semi-metal. So basically, the Weil semi-metal is the material where the quasi-particle behaves as if they were Weil fermions. So this is in the this has been in kind of particle physics, but now this words now transferred to the condensed matter physics, because now we can actually design the material such that the electrons inside of this material behaves as if some exotic particle, like a Dirac fermion, Weil fermion, Majorana fermions. So yeah, so topological band structure, when we have this band inversion like this, we can make this valence band lower than the conduction band. Sorry, conduction band has lower energy than the valence band by some, engineering. And you see there is this crossing point where this crossing point can actually get out when there is spin-orbit coupling introduced. So if they are all fully gapped, like in the K-space, we call it a topological insulator. But because of this the crystal symmetry or time repulsor symmetry or inversion symmetry, depending on the symmetry, this gap opening may not happen at some certain point, which we call Dirac point or Weil point, because Dirac point can split again into two Weil points which has different chirality. So in condensed matter, we have two types of Weil semi-metal, Weil cone, because so one type is this straight cone, like as if it's a Dirac cone in the graphene, or it can be tilted in a certain direction, which is actually not possible because it's violating the Lorentzian invariance. But it is possible in the condensed matter. So this is called type 2 Weil semi-metal, and we learned that this tungsten ditelluride or multitelluride are a kind of type 2 Weil semi-metal. So when we have this two Weil points, there can be this so-called fermionic surface state. Like if you have, so it's like when you have a band inversion, there can be a surface state. That is topological insulator. The band structure is like the bulk is insulating, but the surface is conducting. So same story goes on this Weil semi-metal as well. So although the bulk is semi-metallic, there can be still Fermi arc surface state exists. So people have been looking for this surface state, and actually they are looking for this wild point where they are. So people like APCTP people are kind of pioneers because they can actually see how the band structure looks like. So there has been many APCTP studies looking for this wild point, and also looking for this Fermi arc surface state, which connects these two wild points. But the thing is, this wild point, at least according to the calculation, the separation of the wild point of tungsten ditelluride is very small. They are actually similar or below than the resolution of the current state-of-art APCTP technique. So that is kind of limitation. Some research claims that they have seen this Fermi arc surface state separated to wild point, but later it turns out that they were actually just trivial surface state, and it was not a wild point. So maybe transport can do something about this, because we are not kind of limited by this resolution in K. Although we are in transport, we see the average flow of electrons. So we have some disadvantage, but we also have some advantage. So that's what I want to introduce you, what we can do with this transport, studying the topological materials. Okay, this is another slide for explaining that this, say we have, so for example, if we have this few layer of tungsten ditelluride, then we will have some surface state circling around this material. And so here what we want to do is to make a spark conducting contact on this exotic material and want to visualize how the current actually flows. So if we can visualize how current flows, then maybe we can get some information how the surface state look like. And another one is that when we make a spark conducting contact on this topological materials, this naturally leads to this topological spark conductivity that we are looking for example, for realizing topological quantum computer, realizing Majorana fermions or parafermions. Those exotic quasi-particles can be created by combining spark conductivity and the topological materials. Okay, so recently, a few years ago, an MIT group showed that actually monolayer tungsten ditelluride is quantum spin Hall insulator. So that means it's 2D topological insulator. So it has some etch state circling around. They are quite robust. They can survive up to 100 Kelvin. And 3D limit of tungsten ditelluride, people know that they are type 2 wire semi-metal. So they are expecting some Fermi arc surface state. So our focus is on what happens in between. So when we stack one by one, this topological insulator should turn into topological semi-metal. So what happens in between? It's very naive, but interesting motivation for us. Okay, so I want to also introduce this suspendativity because this is an essential part of this study. So when we cool down the metal below some certain critical temperature, these electrons, they are fermions, they can get interacted through the phonon interchange. So, and then these electrons, which are supposed to repulse each other, can actually combine into a single particle called Cooper pair through this attractive interaction mediated by the phonon. And because we have this 10 to the 23 electrons, macroscopic number of electrons in the metal formed into Cooper pairs, and these Cooper pairs are kind of bosons because there are two fermions get in together. They're boson-like particle, so that they can go into some kind of Bose-Einstein condensation, and these macroscopic number of electrons can get condensed into a certain quantum state. So this is called macroscopic quantum state. So a whole chunk of electron in the metal can be described by just this one wave function, and the phase here, the phase, a macroscopic phase. So when we have two superconductors separated by some non-superconducting material, this superconductor's wave function can leak into another superconductor when the non-superconducting material is thin enough, thinner than superconducting coherence length, then we have some superconducting coupling. So this is called Josephson coupling that Josephson found when he was a graduate student and got a Nobel Prize. So when we have this Josephson coupling, so the supercurrent can actually go flow through this Josephson junction. But depending on the coupling strength, this Josephson junction can flow dissipationless current up to a certain point. So when the Josephson coupling is strong, this critical current is large, and Josephson coupling smaller, then the critical current is smaller. So when we bias larger than the critical current of the Josephson junction, this junction suddenly behaves as if it's just a normal junction. So it will give some finite voltage. So we call this normal branch, and this one is a supercurrent branch. Okay, and this Josephson current is determined by this sinusoidal function of macroscopic quantum phase difference. These two. Okay, so this is basically basic of Josephson junction. And what we can do more is to apply in-plane magnetic field, because in-plane magnetic field can give some Aronoff-Bohm type of phase difference in this macroscopic quantum phase difference. Okay, so these are the called Fraunhofer interference pattern. So because of this in-plane magnetic field can induce this additional phase difference, the total Josephson current through the junction is the summation of supercurrent at each point. This point, this point. So we integrate Josephson current density times sine phi, which we show here, and as a function of x, and we integrate. So this is identical to this optical Fraunhofer pattern that we learned in, I don't know, high school, undergraduate. When we have a single hole, we have this kind of interference pattern. Because of this path difference, we have additional phase, and depending on the angle, we have different the accumulation of the phase difference. So that when we have no path difference, we have the strongest peak, and we have some oscillatory behavior. Okay. So when we have uniform Josephson coupling, say Jx is basically constant. So here x is the width direction of the Josephson junction. Okay. Because the distance now in this non-superconducting material is same, so we can say that Josephson coupling at this point and this point and this point and this point and this point are all the same. So we can draw the Josephson current density as a function of width like this, uniform distribution. So when we put this thing here, then we basically get this Fraunhofer pattern. Looks like a sine x over x. So x-axis is the magnetic field. Okay, so it is the standard shape. And the story changes when this non-superconducting material turns into topological material. So say that this is 2D topological insulator, then the current can only flow through the edges, in quantum spin hole. Then the Josephson coupling will be only here and here, but not in the bulk. So we will have this kind of two delta peak like shape of Josephson current density. And if we put this thing in this integration, then we basically get this equidistant oscillation of the critical current. This is we sometimes call the squid-like pattern, because we get this pattern in the squid that is made by two identical junctions connected by the superconducting ring. Okay, so this technique has been used to show that the mercury telluride and mercury cadmium telluride 2D heterostructure is indeed a topological insulator, so quantum spin hole system, showing that this Etch dominant transport by showing this this interference pattern. So when we have bulk in constant bulk distribution, we have this 1/x decaying Fraunhofer pattern. Whereas if we have edge enhancement of the current in the sample, we will have non-decaying, rather non-decaying compared to this interference pattern. Okay, and similar. Okay.
Question, but the periodicity itself is the same.
Very good point. Periodicity is determined by the area magnetic flux divided by this area. So in this pattern, we have equidistant distance, but in the Fraunhofer pattern, actually we have twice of width of the first law compared to the second and fourth, third and fourth. So this is one big difference, striking difference between these two patterns. But you know, we have to look close to see the difference, though. Okay.
Another question is that the middle,
the bulk.
No. You made the junction and you inserted some insulator or topological insulating material. The distance D in your experiment is much larger than superconducting coherence length or smaller than?
Is it comparable or smaller? It's comparable. It's smaller.
Then my question is that when you insert in the middle topological insulating material, you said Josephson current flow only at the edge. But in principle, Josephson current should flow across the insulator.
Okay.
So that's my question.
Okay. So better metal can have longer Josephson coupling. Let me say, more conducting metal gives stronger Josephson coupling, and less conducting material gives weaker Josephson coupling. So actually, the length to scale we have to compare is the superconducting coherence length in the metal, which is determined by the metal's property. So in metal, they have longer superconducting coherence lengths, so they have a greater potential to have stronger Josephson coupling, but worse metal gives smaller Josephson. That is, yes.
But originally, when Josephson suggested this kind of phenomena, he imagined the
thin insulating
layer rather than metal.
Yes. So original Josephson junction that Josephson suggested is called tunneling Josephson junction. That there, insulating material is just a vacuum. So it depends on the tunneling property. But now this Josephson junction is so-called proximity Josephson junction. Now the insulator is replaced by this metal. So this metal can give stronger Josephson coupling with a given same length. Okay.
Thank you.
Yeah. Within this metal, depending on how good the metal is, the Josephson coupling will be different. So basically, insulating bulk will not give much Josephson coupling, whereas the metallic edge will give stronger Josephson coupling. So Josephson coupling density will be integrated, turned into this Fraunhofer pattern, which we can experimentally measure. Okay, so what we measure is this, but what we want to know is this. Okay, yeah. A similar technique also has been used by Professor Hu Jung Lee's group. They made the Josephson junction with 3D topological insulator. So in 3D topological insulator, all the surface is conducting. So if we see the side view of this cut, then this blue, green one is the insulating bulk, and the blue, sky blue area is the conducting surface. So what we do is this aluminum Josephson junction is made like this, and we apply vertical magnetic field. Okay, so to the point of magnetic field, you are seeing from bottom to top. Okay, you are kind of integrating z-axis. You know what I mean? So for the magnetic field view, the current density will look like this. Okay, this is with direction. So from the bottom to the top, you imagine the bulk. There are still top and bottom surface state. Okay, but they will be added. But on the side, there will be also side surface state, which will be integrated through all the thickness of this tungsten topological insulator. So that's why we also can expect etch enhancement of Josephson coupling even in the 3D topological insulator, not only in the 2D topological insulator. So that's how they measure. This is Josephson interference pattern as a function of magnetic field. So the green one is the ordinary Josephson interference pattern, which decays 1/x, whereas this red line is the fitting of this measured data. They are rather not decaying, but rather persist even up to the critical magnetic field of the superconductor. Okay, so this is very interesting technique that we can do. It's like mimicking, I don't know, the transport can actually do some visualization. If I say.
So you're using, this component to this material is connecting both of them.
Mm-hmm. Mm-hmm.
But is it really necessary to use this component? Because that's what we have to do with resistivity.
Mm-hmm.
And for example, void dependent enough to
I see. So you mean the, say, conductivity as a function of thickness?
Yeah.
Something like this? Yeah, that is also has been used. But, you know, they are all in different crystals. So they should be measured in different devices. Right? So assuming they are all different, but only the thickness are different, then maybe we can plot the thickness and conductance and interpolate it, and maybe why, you know, this intersection, maybe contribution from the surface state. That's what people has been doing, but they have some, you know, limitation, the consistency of the but this one is done in a single crystal, that crystal. Yeah, that's what. Mm-hmm. Yeah. Mm. Yeah. Mm. Mm. Yeah. So the ability of this kind of resolution actually comes from the extreme sensitivity of Josephson coupling on metallic property. If it's little less metallic, then suddenly Josephson coupling is just gone. And if it's a little bit more metallic, suddenly Josephson coupling pops out. So yeah. All right. So the system we want to study was, again, come back to the tungsten telluride, was tungsten telluride. So yeah, people, you know, including me, has been working on this graphene for a long time. So graphene is, you know, beautiful material. It has very isotropic Dirac. So I am kind of get used to work with this kind of material. So I initially, when we started this study, we just forgot about the anisotropy in tungsten ditelluride. So if you see the crystal structure in tungsten ditelluride, this is tungsten backbone here. So tungsten backbones are closely located along A-axis, but they are loosely connected through along the B-axis. Okay, A-axis, B-axis, and then this AB plane is stacked to the C-axis to make a bulk. Okay, this is layered material. So the conduction along A-axis is much stronger than the conduction along B-axis, and that naturally, you know, transform into the band structure, right? band structure should be also very anisotropic. They should be squeezed or tilted, you know. Okay. And another, okay, this may not be, okay, wait. Tungsten dietal has two different categories of the structure. It's 2H structure, TD structure, but you don't have to worry about this one because this is unstable in nature. So when we grow tungsten dietal, it's most likely TD structure, which is, if you see, according to the calculation, is metallic, it's semi-metallic, whereas 2H structure is insulator or semi-metal. Okay, so we will work on this TD tungsten dietal. Okay, so first of all, because of this anisotropy, we have to track out which direction is the A-axis and which direction is the B-axis. So we initially mechanically exfoliate tungsten dietal using Scotch tape like this, and the initial crystal is actually needle shaped and it's longer along A-axis because, you know, the interaction, the distance between tungstens are closer. And then we can track out which direction is A-axis. And then Yongbin carefully put this tape on the silicon substrate and stretch it out and take it out. Then some flakes will remain on the silicon substrate, just like we do for graphene. And we just know that axis is, this one is along A-axis, or you see this is the device, and this is A-axis and this is B-axis. Okay, it is not obvious in the optical microscope, but we know the axis direction. So we will name the junction A junction and B junction. When Josephson current flow along the A-axis, we call the device A. And if the Josephson current flow along the B-axis, we call device B. To be more precise, we also got help from Jong-Wan Kim at Postec to do this polarized Raman spectroscopy to map out which direction is actually A. And we were right. We were right. So A-axis that we expected was actually A-axis, and B-axis vice versa. So we initially want to confirm the anisotropy of the conduction because A-axis will give more conduction. So these are all normal metal electrodes, and we measure the resistance along this direction by applying current like from here to there and measure the voltage between this and this. We did the foolproof measurement to get rid of the contact resistance contribution. So if you see this, the theta is the angle between A-axis and the measurement axis. So at 0-108 degree, we have lower resistance, but higher resistance at 90 degree and 270 degree. And we have kind of order of 3 anisotropy of 3. So they have kind of 3 times difference in the conductance. Okay, so this is all verification that we got the right tungsten dietal, right? And we measure the Josephson current interference by applying magnetic field and measure the critical current. So this is the differential resistance map. So the blue region is where the Josephson current flows so that no dissipation happens. So that differential resistance is 0, which is colored by blue. And these are resistive state. So the boundary between the blue and non-blue area is the critical current. So you see that it's rather monomer X decaying behavior in the Franov pattern for device B, but for device A, where the Josephson current flows along A direction, gives non-decaying Franov pattern. So yeah, so it's supposed to decay somewhere like this, but it kept going. It kept oscillating at higher magnetic field. So you see that this is 200 Gauss, but this one is 40 Gauss. They decay very fast, whereas this one persists oscillating even at the high temperature, high magnetic field. So that we can infer that there might be some etch enhancement in the current. Okay, the similar measurement has been done for many different devices, because different devices may have some difference. So we want to check the consistency. So all the B devices are rather decay faster compared to A devices. They are persisting up to relatively high magnetic field. But it cannot persist up to infinite magnetic field because the superconductor will be killed by the magnetic field at some point. Okay? So to be more quantitative, we want to evaluate the current density from the measured interference pattern. So we integrated Josephson current density and get the front of pattern. So what we can do is to do the Fourier transform the measured interference pattern and get the information of Jx. Okay, so this is the equation that I showed you before, but we can also make this sign into e to the I phi and get the imaginary part. And this is basically Fourier transform, right? And then we can basically do the inverse Fourier transform to get the Jx. And the blue one, this one is the interference pattern that we experimentally measure. So for example, this is just an example. This is a textbook front of pattern that we generate. And then so what we have to do is actually one thing we have to assume is we have to recover the phase information. Unfortunately, because of this, this one, sorry, because we will lose some phase information, we have to kind of assume. But this assumption is rather, how do you say, well received. Yeah. Basically, this is what we can do the best. We can not do the better. Okay. So we first recover the phase information. This is the 0 phase and this pi phase, 0 phase, pi phase, 0 phase, pi phase. And then we inverse Fourier transform and get this uniform Josephson current density. Okay, this is just a practice. So what we did is just did this inverse Fourier transform analysis on the measured critical currents. So this is measured data, and we recover the phase information, assuming this is 0, 0 pi, 0 pi. We can just flip, and then we basically get rather a uniform current density. Whereas the non-decaying interference pattern we got from a device like this. This is IC extracted from this color plot, and we flipped the phase and did this inverse stress transform, and we actually see this spiking peaks at the edges. This edge enhancement was qualitatively expected, but this is kind of quantitative analysis and see how much the current is enhanced at the edge. So estimation is about 15 nanoamp and 40 nanoamp. All right. So, okay. So to do another sanity check, we want to do the same experiment with graphite device, because graphite is considered to be non-topological and just a simple plain metal. So we do the same fabrication that we did for tungsten dictelluride and did the same analysis, and we don't see much clear etch enhancement from this one. So that we were kind of relieved that our fabrication doesn't give faulty etch enhancement. Okay, this is one sanity check. So to sum, we have A-axis and B-axis in this flake, and if we cut along B-axis, then we see the current flowing along A-axis. Then we see the enhancement, right? But B-axis device, like this, B-axis device corresponds to this cut. Okay, we cut along A-axis, then we see the current flowing along B-axis. Okay, then we didn't see any enhancement. So that was very puzzling. If there were any surface state, they should be everywhere, like a 3D topological insulator, bismuth telluride, so forth. So, but you remember that this material is very anisotropic. So hopping Tom along A-axis is much stronger than along B-axis. Okay. So qualitatively speaking, even if there were edge state along B-axis, flowing B-axis, they can hop into the bulk much easier because that hopping is along A-axis. Okay, now I'm starting to be confused. Okay, right? Again, so if there is a B-axis edge state, they have more tendency to get merged into the bulk because that merge happens along A-axis. Whereas the A-axis surface state are better localized compared to the B-axis. That was kind of quantitative expectation. And then I found a big law at the HKUST to do the model calculation to show quantitatively that is really the case, and that was really the case. Okay, long story short. Okay.
You said this material, tungsten telluride is bimetal.
Mm-hmm.
In this, especially this cartoon picture, how do you expect such edge state from bimetallic state?
We expect okay, surface state. Okay. Even though in addition the bulk is also semi-metallic. Okay, so this is hard material to visualize the current flow because bulk is conducting plus surface state is also conducting. Okay, so this is the situation. But as I discussed you before, so for 3D topological insulator, because we apply vertical magnetic field, we integrate along Z-axis or C-axis.
Yeah.
Okay, so we don't worry too much about actually top and bottom surface state, but we only care about this edge surface state. So this is the situation.
Why you don't worry about the top and bottom state?
Because they will look as if they are bulk states in our experiment.
Okay.
Yeah, because we only can see the integration along C-axis. Yeah. So the top and bottom surface will look just like they are in the bulk state.
So they contribute to Josephson current.
Yes, they contribute here.
I see.
That, yeah, they should give some contribution here, but for now, we are not much interested in that quantitative contribution. Okay. And here I want to emphasize that this technique is powerful because we can differentiate. We might be able to differentiate surface state even the bulk is conducting, because we can quantitatively show the distribution of current flow. Okay. So this is just storing, I think, strong point.
Do you know the thickness of the material?
It's like 10 to 20 nanometer.
So can you control that thickness? You can do that different.
Yeah.
Thickness?
Yeah, of course we can do. Yeah. But please mind that for different devices with different devices can have different quality of superconducting coupling. So the different devices, it's better not to compare different devices quantitatively. Yeah. So that is weak point better. Yeah. If we can in situ control the thickness, that would be nice. But yeah, we are not there yet. Yeah.
I think your point here is that we can distinguish between the bulk and edge.
Edge, yeah, yeah. And if we apply in-plane magnetic field, then what we will see is integration along, say, B-axis. And we can make another devices along different orientation. We apply magnetic field along B-axis, A-axis, then we will see the integration along A-axis. It's like we see the shadow of some 3D object with different angle. And maybe we can reconfigure into a more complete 3D map of current flow. That is still kind of science fiction for us, but that will be awesome if we can do. Yeah, rotating devices. Yeah, that is our vision that we want to pursue. But for now, we are just applying magnetic field along Z-axis. So
reproduction is also anisotropic.
yes,
Etch is also.
yes,
Both
anisotropic. Yeah, both are metallic and anisotropic. Yeah. Well, this experiment started as just a kind of naive motivation. We know we have this kind of Josephson interferometer technique, which can visualize current flow, and have done some similar experiment in 3D topological insulator. Why not we do with this wire semi-metal, where people expect Fermi arc surface state. Yeah, but related this topic, if you remember the wild point in at least according to the calculation, the wild point of tungsten dietal are barely separated in K-space. That is separated less than the resolution of RPAS. But later, theorists came out new idea called higher order topological insulator. So basically, when this closely separated wire cone get annihilated by themselves, then it will open another gap. Okay, the wire point open. So okay, wire point was given by the band inversion and gap opening. That is kind of first topological insulator phase transition. So that we have this Fermi arc, we can expect Fermi arc surface state. But in this material, the wire point are not so well separated. So in realistic experimental condition, they can be annihilated or partially annihilated. I don't know, it's not known. Then this wire point initially protected by some symmetry can open a gap again, second order opening gap. So then the Fermi arc surface state will gap out again. So 2D Fermi arc surface state gap out again. So the 2D surface bulk is now insulating, but only the boundaries will be conducting. So if you imagine that this is in 3D material, so this resultant conducting channel will only remain on the hinges. Okay. Yeah, this is how I understand the topological insulator that I learned from theorists. Yeah, so that's why this material is kind of optimal material to study HOTI, because wire points are barely separated. And Professor Gil-Ho and colleagues are also interested in, kind of calculating how to, manipulate the distance between this wire point so that we open again, close the gap, phase transition from first order TI to second order TI. This will be very interesting topic. Yeah. All right. So yeah, we learned, okay, tungsten dietal was HOTI. Can our experiment say something about it? So we were discussing with theorists, and they set up some model Hamiltonian to describe our TD tungsten dietal crystal. Okay. To be actually precise, for those who actually know a little bit more, I have to be honest that in bulk crystal, usually the crystal tungsten ditelluride are TD phase, which looks like this. Okay, these greens are tungsten and these purples are telluride. But they can also have this 1T prime phase. And they are, if you see layer by layer, they are identical. But they are slide a little bit differently. So that unit cell here is, okay, I don't know this in English. 평행사변이요. Parallel. This is a little bit skewed. Yeah, parallel. Okay. Yeah, this is so they are a little bit different. But you know, this crystal is central symmetric, but this is non-central symmetric. So symmetric wise, there might be strikingly different. But we did the calculation for 1T prime symmetry, to be honest. Because previous theorists predicted HOTI in 1T prime phase first, and also they discussed about the HOTI, possible HOTI phase in TD phase, but they are rather focused on 1T prime. So our justification is that as far as we can deform this 1T prime phase to TD prime phase adiabatically, such that the bulk gap doesn't close, then topological nature will be the same. Okay. When you're deforming the structure a little bit, if you don't close the gap or open the gap again, then topological nature will not change. That's our justification. Okay. Frankly speaking, I think that is still open question, how the HOTI phase stabilizing non-central symmetric crystal. But anyway, we did the model calculation for this 1T prime phase. A little different crystal symmetry, but we believe they are basically in the same crystal, basically in the same topological group. Mm-hmm. And this is the model calculation result. So we see hinge state along a-axis, and we see not so clear hinge state along b-axis. Again, this is because the anisotropy of the hopping. So because we have more hopping along a-axis, this b-axis hinge state merging into the bulk. So we can tune this hopping parameter and see actually that is the case, and that was indeed the case. 1T prime phase. Yeah, T prime phase. That with the central symmetric 1T prime phase. Yeah.
I mean, is it possible to do some more computation for TD phase?
That I actually don't know. Yeah. Can we? Because of this non-central symmetric property, the calculation load will be vastly increased, I think, because lack of symmetry. I don't know. Yeah. Any?
Because you can check your conjecture, right?
Yeah, conjecture whether it's really the case or not. But okay, this is rather non-scientific, but the theory calculated this central symmetric easier problem. They had to do the calculation much smaller lattice size to do it in humanly possible way. Or current, yeah. Yeah, this is what I want to look for the help, whether this non-central symmetric rigorous calculation is indeed possible or not.
For symmetry-wise, these two phases are totally different. One
yeah,
inversion
symmetry.
The other no inversion.
Mm-hmm. Yeah.
Totally
Yeah.
different.
Yeah. To be.
For example, you may not allow spin-orbit coupling in the case of
Spin-orbit coupling.
Spin-orbit coupling satisfy inversion symmetry.
It's not.
It violated inversion symmetry and it satisfies time reversal or vice versa. Yeah, Gil-Ho Memorial. Spin-orbit satisfy time reversal, but break inversion. I'm confused. You said your model simulating central symmetric phase. So central symmetry means it should have inversion symmetry. Then can you introduce spin-orbit coupling for
non-central symmetry?
That's what I thought. So anyway, you can check.
Maybe we have different kind of vessel. See, introduce Anisotropic. Sorry.
Hard to imagine. Once you have combination of spin multiplied with momentum, that's basically spin-orbit coupling.
Yeah.
Then on the inversion, spin
flips
and also momentum flips. So spin-orbit coupling satisfy inversion symmetry. The spin-orbit then violate time reversal. Anyway, spin-orbit coupling means you should satisfy inversion symmetry. Oh, you are right. So then that's why we have to only simulate the central.
Yes.
symmetry.
Yes.
You cannot simulate non-central symmetry phase with the spin-orbit.
Oh, okay. Okay.
You have to introduce some other term which break inversion symmetry to simulate this second phase.
Okay. Okay. Yeah. Because of this subtlety, we initially want to lean onto central symmetric cousin. Yeah. But this is, I would say this is open question. Non-central symmetric HOTI. Okay. Sorry. So maybe you can already imagine that whether in Fermi arc surface state scenario, all the surfaces are conducting, or HOTI hinge state scenario, only hinges are conducting. Basically, we cannot differentiate these two scenarios because we only see the integration along z-axis. If you see from bottom to top, the Fermi arc scenario will give edge enhancement, okay? But hinge state scenario also will give edge enhancement. So this is basically the referee's criticism at the first round. And then, right, you're right. We need some more experiment. So we prepare a control experiment. Of course, if we can do this shadow, description that I discussed, like z-axis, a-axis, b-axis, and visualize this, but that is not possible in current technology. So we made top only contact Josephson junction. This is control experiment we pursue to convince people this is indeed hinge state. So what we did is we etched, so this is tungsten dietal, right? We etched the side and fill it with aluminum oxide insulator like this. This is side view. So we etch here and put the insulator right away so that we just screen out the bottom surface like here and here. And then we put the superconductor. So previously, the niobium superconductor covered all the side and top and bottom hinge, but now we are separated from the bottom surface state and the bottom hinge state, if there is any. So if we draw the diagram again, in the hinge state scenario, we only couple to one of the hinges. But in the Fermi arc surface state, we still couple to the side and the top. So this will not give much difference that we did in the early experiment. So this is expected current density profile. So this is what we exactly expected in the previous experiment. But this one will have only one side enhancement. One side enhancement will not allow the interference between this and this current, Josephson current, so that it will come back to the usual shape of front of pattern, whereas the Fermi arc state scenario will still give non-vanishing front of pattern that we measured before. So we call this AT, and I don't know why it's called AT. Okay, anyone. So this is previously measured non-vanishing front of pattern that we claim the side surface. And this AT is this control experiment. And this one just decay rather fast, as if it's BX's device or graphite device. This is just one of the control experiment results. We also, did three more devices test, and we see the consistent result. So that's how we finally kind of convinced referee that this is okay. We have to tone down this. This looks like it's hinge state, okay, rather than surface state. Okay, we have to be always conservative to be safe. Okay, so doing this kind of funky, funny experimental configuration, we want to verify whether it's hinges really HUTI phase or just Fermi arc surface state that we expect in the Y semi-metal. So now we are working on Shapiro step measurement. So this is ongoing experiment. So in this transport community working on topological materials, what we do is make a Josephson junction. And if this Josephson junction is mediated by topological surface state, where the spin and momentum are locked together, then we basically call this one as a effectively spinless system. Because if you know the K, you automatically will know the spin. Okay. So in principle, in Hamiltonian, you don't have to write down the spin, because you know anyway. If you know the K, you know the spin. So spin is not an important quantum number. It's dissolved in K. So this is effectively spinless. Of course, we cannot get rid of the spin of the electron, but we can make this effective spinless system. And this effective spinless system, when it's combined to the, say, S-wave superconductor, it can generate some P-wave component superconductivity, which is potentially interesting looking for Majorana fermions and topological superconductivity study. Okay, so this hinge state is also helical. This is basically, this is just like the Etch state of the quantum spin Hall insulator, although they are only at the hinge. So to prove this is indeed helical hinge state, we want to show the Shapiro step behavior. Okay, this is long story short, but basically when you have this spinless system and you make Josephson junction, then your Andre bound state mediating Josephson coupling between these two is now 4 pi periodic. This is macroscopic corner phase difference, and this is the Andre bound state. So so usually ordinary Josephson junction has 2 pi periodicity. So just like the, in Josephson current was IC sine phi, and IC sine phi is 2 pi periodicity, periodic. So this is usual Josephson coupling. So that is this red dotted line. But when you have this spinless system mediated, then you start to have this two gaps is close together, and this line and this line will have different parity. So they will not mix together. So now the under bound state is 4 pi periodic. So your Josephson current relationship is not sine phi anymore. It's now sine phi over 2. So this periodic doubling gives Shapiro step doubling. So, okay, Shapiro step is the DC voltage step in IV curve when you shine the AC microwave excitation. So this is kind of resonance between AC microwave voltage source and the Josephson coupling, AC Josephson coupling. Okay, so we usually get the integer step in the voltage like this. The step is proportional to the microwave frequency, and that is should be integer. But now, because of doubling of periodicity, this step will be doubled. So that means we will lose odd number step in IV curve. So you see that this is one example of people measured in quantum spin Hall Josephson junction. You see that this is step 1 is missing. The red one is straightly go to step 2 and 3, 4, 5. Whereas at higher frequency is 1, 2, 3, 4 ordinary step. So we call this one all the step missing or step doubling. Okay, this is again signature of topological spontaneity. So we did the same experiment. We also in tungsten dietal, we also see the doubling of Shapiro step. We don't see the step here. Okay, I would admit that this is still marginal, but we are still improving the signal quality and measure many different devices and consistently observing similar behavior. Okay, so when the microwave frequency is getting larger and larger, then it goes to the ordinary step. That is explained by another scenario. So this is not the main point. So my point is, we can see the odd step missing. That is again signature of topological hinge state. All right. So we studied tungsten dietal, that is known to be type 2 wire semi-metal, but wire cones are very separated. So maybe they are already kept out in nature and giving the hinge state. So what we did is to make Josephson junction and measure the interference pattern to get the information of current flow. Although they are all integrated along C-axis, we can do some control experiment, top-only contact experiment, to give some evidence of the higher order topological insulator phase in this tungsten dietal crystal. So the further study, for example, the Shapiro step is needed to firmly confirm that is really the case. And also my hope is that this study can get more attention from various experimentalists using different technique. For example, STM, for example, can actually map out the surface state. The STM people said that resolving hinge state is kind of tricky because Etch is always non-trivial to study on. But if we can give, good enough motivation, maybe they can be convinced and work on this hard experiment. All right. So this is it, and thank you very much.
Okay, question.
Actually, I should ask you this question in the meeting. The last topic, the 4 pi periodicity, the Shapiro step signal. By the 4 pi periodicity, you want to prove the emergence or existence of hinge state. The question came up to me at the moment ago is that I wonder whether or not you can tell by the full pipe periodicity, you can tell between the hinge state and topological hinge state and the topological edge state. Can you tell?
That is exactly the question I've been afraid of to be asked. I think we cannot distinguish Fermi arc surface state and the hinge state because they are all speed momentum lock system. But
What about the strength of the step or
yeah.
the side of the step?
Yeah.
There should be any
difference. There should be some difference. So this 4-pi periodicity happens only when there is X momentum component. So it can happen only in 1D system, precisely speaking. If it's 2D spinless system, if the Josephson coupling happens only along the junction, so electron goes, hole coming out, electron goes, coming out, or if this quasi-particle has only x-axis component, it will give 4-pi periodicity. But if it has some y-axis component, it will open again. So it will give 2-pi periodicity. Compared to Fermi arc 2D surface state, 1D hinge state, they are forced to move along one direction. So it's more advantageous to give 4-pi periodicity. So signal should be stronger.
maybe
More disorders and yeah, because disorder can introduce y-axis components in the 2D state. But the reason why I tell you that we cannot distinguish between these two is because still 2D Fermi arc surface state can still gives. Yeah. So yeah. So just seeing 4-pi periodicity only with that may not be able to distinguish these two scenarios, but we know that hinge state will give stronger signal in 4-pi periodicity. Yeah. Experiment is not always perfect. Very important question. Yeah.
So I mean, those two scenarios, whether it is high order potentiator or whether it is wide signal with Fermion, so this is quite different object, right? One is the balcometer, also subcometer. So that hand is the high order potentiator is the insulator.
Oh, sorry. So I give you a misconception that topological high order topological insulator in Tungsten Dietal, right? Doesn't mean the bulk is insulated. I think we have to come up with better naming for higher order semi-metal. Something like topological, higher order topological semi-metal. Okay, I want to get the opinion from theorists who initially made this term, but it means that higher order topological insulating phase in Tungsten Dietal, right? But it doesn't necessarily mean the bulk is insulating like 3D topological insulating.
So the bulk is
Still
insulating, but there is no surface state, but only heat.
so we expect bulk is semi-metallic, still semi-metallic, but the 2D etch is insulating, but only hinge state. Hinge is conducting.
Is it possible? Strange combination. Bulk is still semi-metal. Surface is
Insulating, but the
only
hinge is
metallic. Who says so?
Nobody says so far.
Just
But
your imagination.
yeah, this is our speculation.
The referee accepted this very strange scenario.
Well, I think it's Why not? Why not possible? It's strange. It's strange word.
Oh,
This world is.
it sounds impossible.
Or even if the rules are insulated, both basically
Actually,
in reality.
in reality,
It's only reality. In theory.
even in theory.
Or in principle,
Mm.
bulk should be insulated in order to produce this hinge state.
Well, okay. So to get the well localized hinge state, we have to get the bulk state, insulating bulk.
Yeah.
But even with the existence of the bulk, metallic bulk, the hinge state can still be there. Only they will be rather less localized. Like in topological insulator, here we only have surface state, but here we have bulk state and surface state.
Oh.
But the surface state and the bulk state are closed in K-space. They have more, the surface state will be delocalized into the bulk in real space. So this is our
You
picture.
are saying the bulk state has gap, but only because the chemical potential just
Crossing here,
outside the gap, so practically it's
metallic,
metallic.
semi-metallic. Yeah.
But in principle, the band structure itself should have a full gap.
Ah,
You're saying just the chemical potential accidentally cross.
So maybe we can turn this question to, if we can tune the Fermi level very precisely, can we make the bulk insulating, surface insulating hinge conducting?
Yeah.
I think
That's the ideal case.
but okay, yeah, that is the ideal case, but okay, now I am not quite sure, but there is two. Yeah, I think so. I think it should be possible, but only thing is I think in principle we can make the bulk insulating by tuning the Fermi level. Yeah, I have to ask Mazali to grow better crystal. Yeah.
Any other question? Professor Chong, you should ask. No question. Let me ask some participant. Hello, participant. Is there anybody who want to ask a question to this very interesting talk? If you don't ask a question, I will point.
Hello.
Oh.
Yes. Yes. Please.
Hello. Can you hear me?
Yes, clearly.
Yeah. I actually have a question.
Yes.
So you said that when the bottom is blocked, then you saw that the hinge state is only localized at either left or right. Am I right?
Yes. When we block when we block the bottom, we couple to one of the hinge state only. That's the point.
So then I'm actually curious, when when the bottom is not blocked, was there any case only one hinge was observed?
I'm sorry, can you repeat?
So usually when the bottom is not blocked, then we should see the hinge state at both left and right. But
yeah,
was there any case only left hinge was observed or only right hinge was observed, even the bottom was not blocked? I'm just curious because I recently saw a paper that theoretically it is possible. So
maybe I didn't get.
Leave the right bottom hinge, but the upper left hinge blocked. The other way.
I still.
So when the invergent symmetry is broken, then there is a possibility of seeing the hinge state at the left top and the left left bottom.
Ah,
So
is that so? Okay, that's
so I'm just curious. By accident, did you guys saw such situations or not? I'm just curious.
okay. That is. We still have no ability to differentiate left up, lower down versus left up, left down. We
we can just know it by the distinguishing just left and right. So what I'm saying is that when you guys don't block the bottom, was there any case that only left was seen?
So for example, can you see?
I see the blackboard.
So maybe you are saying that make a Josephson junction here and make a Josephson junction here. We see only Hinge state here, but not here, something like this.
Yes.
Yeah, we are actually doing this kind of experiment. Although we didn't expect that scenario, but Yongbin may can. You don't see? Okay. We don't see this behavior yet. I think, we haven't focused on whether it's that scenario, whether that is true or not. We even didn't know about that scenario. But that is interesting, control, more exotic experiment than we can pursue. Sometimes what it actually happens is that when we make two Josephson junction in this side and that side, each Josephson junction may have different contact quality to the crystal. So they may give some different behavior, even in a trivial case. So we have to be very careful. But maybe we can design some clever way to distinguish that scenario in some other way. Thank you.
Okay, thank you.
Yeah.
Okay. Found when I said our pinpoint the participant, many people disappear. 강정수 교수님, 들리시나요? 강정수. Professor Kang, could you ask some question? Okay. Okay. So,
I actually have another question.
Okay, please. Oh, I'm sorry. Who can you? What is your name?
I am Chiho Yun Chiho.
Okay.
Yeah.
Thank you.
I in the previous slide you mentioned that tungsten telluride has two phases. One is 1T prime and another one was TD phase. Am I right?
Yes.
So the phase you did experiment was TD phase, right?
Yes.
And the TD phase lack invergence symmetry.
Yes.
So can I just regard TD phase as a phase which have lower symmetry than 1T prime, or it has some other symmetry which 1T prime doesn't have?
It has different phase, different symmetry.
What is it?
Okay, TD phase. Okay, TD phase have C2B and MA, the mirror symmetry.
So what is the symmetry that TD phase have, but 1T prime phase doesn't have?
It's glide. How do you say glide symmetry? Okay, I'm sorry that I may not be able to answer correctly, but you can find the paper from Pablo Herero's group, and they categorize the symmetry of 1T prime bulk and TD bulk. It's the lacking of some symmetry of 1T prime. It has different symmetry. Which
okay.
believe one of them was gliding symmetry. What? Okay, from that point, I actually don't know what they are meaning. Sorry. Yeah.
Okay, thank you.
Symmetry. It's not just a small lower symmetry.
Okay. Good. Thank you.
Thank you.
Okay, so I think it's time to close. Thank you very much.
Thank you very much. Thank you very much.